All right, so this is your notes on carbon and biomolecules. So you should have your note packet out that I gave you in class today. And remember, please, that we are only going to do the first page front and back, and then one more page front and back. So it shouldn't take too long. So I have something to write with, your notes and highlighter. All right, so we're going to start with, obviously I said it's carbon and biomolecules. So carbon, why is it so important? Why do we care about it? Carbon is one of the 6 elements of life. So it's the first one, probably the most important one, because all organisms are carbon-based. So out of the 6 elements, carbon is going to be the one we use the most. But we're also made of 5 other elements. Hydrogen is going to be one of them, nitrogen, oxygen, phosphorus, and sulfur. So if you need to, take a moment, pause it, and write this down. The most important element, I already said it, and before I do that, I will from here on out refer to these 6 elements as CHNOPS. It's easier than saying each one of them out. So CHNOPS stands for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And now the most important element out of all 6 is going to be carbon. Again, all life forms are carbon-based. We can only really imagine carbon-based life forms. No other element on the periodic table, and there are a lot of elements, no other element on the periodic table fits kind of what carbon needs to do. It doesn't kind of meet the requirements. So let's talk about carbon a little bit. Why do we care? Because carbon-based molecules make up organic compounds. And organic compounds are what you build your body with. So if it contains carbon and hydrogen, it's going to be considered organic. If we just have carbon, it's not organic. Like CO2, carbon dioxide, is not organic because it doesn't have any hydrogen in it. So let's review the atomic structure of carbon. I know there is a box on your notes, but you are going to write down the protons, neutrons, and electrons. Don't draw this in your box. So we know we have, if we look at this, we have 6 protons, because that's what the atomic number right here means, 6 protons. If I take the atomic mass, which is the protons plus the neutrons, and subtract the number of protons, it's going to give me 6 neutrons. And then I will have 6 electrons because I should know, or you should know, that the number of protons and the number of electrons is going to be equal in a unbonded atom. And then we have to answer a question. How many valence electrons are in carbon's outermost orbital? So let's take a minute and draw it. So in the box to the right, you're going to draw carbon. In the nucleus, instead of drawing all of this, you can just draw a circle and put 6p for protons and 6n for neutrons. But do please draw the orbitals or the energy levels around the outside. And the question is, how many electrons are in carbon's valence or outermost orbital? So the one furthest from the nucleus. And as you do your drawing and look at the diagram here, you should see that the answer to that question is 4. And we should remember that sometimes, even though atoms have a certain number of valence electrons, they want to get to a certain number. And that for us is the magic number of 8. So if carbon has 4 valence electrons, 8. So how many more electrons does carbon need to be stable? It's going to need 4. And that means, guys, that it's going to, in order to get these electrons, carbon is going to have to interact with other atoms. It's going to have to bond with other atoms. And that becomes very important because that's how we build the molecules of our bodies and of our cells. So carbon is, again, great at doing what it does, and there are some reasons that it's really great at doing what it does. And the first one is the most important, so after you write it, I do want you to highlight it. Carbon can form 4 bonds. They will probably ask you that on the keystone. This is the only one I need you to memorize, that carbon forms 4 bonds because it needs those 4 electrons. So in order to get them, it needs to have 4 different bonds with 4 atoms. We know that carbon is a small atom compared to other atoms in the periodic table with its 6 protons, 6 neutrons, and 6 electrons. It's one of the smallest that exists, so it allows it to kind of be more versatile. And carbon is going to covalently bond to other atoms because it inherently likes to share electrons. It's not small enough that it gets electrons pulled away from it for ionic bonds, and generally, and it's not strong enough that it's going to be able to really pull electrons away from other atoms. So it likes to share, and it likes to share nice and evenly with other atoms. And because of those three properties, 1, 2, and 3, carbon can actually build many different shaped molecules. So molecules are three-dimensional. We often don't realize that, but they have a 3D shape, and they can be a couple of different ways that we can categorize it. So the first one is linear, which are straight lines. And you have this picture on your notes. So this is a straight chain or a linear chain. So you have a whole bunch of carbons in a row surrounded by hydrogens. We can also form rings, which really are not rings, they're pentagons or hexagons, and this is what they would look like. And our last one are branched chains. So this one's going to look similar as a base structure to your linear chain, except we've added some branches of more atoms off of the actual central chain. So we can have linear, rings, or branched. So besides carbon, who does carbon like to bond with? Carbon can bond with lots of different things, but for our purposes, we have 5 that we are concerned with. First one is hydrogen. Notice I put 3 stars next to it because carbon and hydrogen love each other. They love to bond, and they love to bond in biomolecules, the molecules that make up cells. So hydrogen is super important. I would highlight that one. And then if you notice, there are 4 more spots, and they should be maybe what you might be guessing. So oxygen, nitrogen, phosphorus, and sulfur. So carbon, for our purposes, really likes to bond with the 5 other elements of life out of CHNOPS. And if we look at your periodic table, you should notice that every single one of these are nonmetals. So they're in that nonmetal category, meaning if I'm bonding any of these to any other on the list, so any of these 6, no matter what combination I pick, they're going to form covalent bonds. So they're going to share electrons. These are strong bonds. They're going to hold tight. They're going to keep you together, which is important if we're talking about cells. We don't want something that's going to very easily come apart because that's not going to be good for life. We need these molecules to be strong and stable. All right, so we've been talking right now about the 6 elements of life, and they're atoms, really. And we know from levels of organization that atoms build molecules. So we have to take these and start putting them together to build larger structures if we're talking about levels of organization. So atoms build molecules, which build organelles, which build cells. So we want to get to that cell part, which is life. So again, we're continuing on our notes. So these are elements of life, but these elements are used to build 4 major biomolecules. And you might have heard of some of these before. Carbohydrates or sugars. And a lot of these sound like foods, but we actually use them in our bodies for actual biological functions. Lipids or fats. And this is not just like body fat, like, hey, I gained 5 pounds, I have more fat on me. You have lots of lipids inside your body that do lots of diverse things to keep you alive. Proteins. And our last one are nucleic acids, which we would generally say is DNA. It's not the only one, so I definitely need you to write the word nucleic acid, not just DNA, because DNA is an example of a nucleic acid. So these are the 4 we're going to be spending some time talking about. But I have to build them. So these molecules are pretty big molecules compared to, just if you had a single carbon atom or a single hydrogen atom. So these are big molecules. And we have to build them, and that takes some, we need the things, we need the raw materials to build them, and we need the energy to do that. So we have some vocab. So a monomer, the prefix mono means 1. These are simple molecules that are created when CHNOPS bond together. So think of it like if you looked at a tile floor. The tile floor is the whole structure, and each tile would be a monomer. It's one piece. Or like a Lego. You can have a whole bunch of Legos that each by themselves are one piece that you can use to build something larger. And what we are trying to build out of monomers, if we take a bunch of monomers and put them together, is polymers. We're trying to build polymers. The prefix poly, P-O-L-Y, means many. And what we're really referring to is the many monomers joined together to make this larger structure. And here's just a picture to again familiarize you with these words. So monomers, you would have 3 here, 1, 2, 3. Each of them is an individual piece. They're a subunit or a building block. And I can put these pieces together in many different combinations to build larger structures. And not only can I build larger structures, if you've ever played with Legos before, these larger structures can also be broken down back into monomers. So it gives your cell versatility. It can use monomers to build something larger, or it can break down larger molecules into the monomers in order to use them again to build more things. So how do we actually build? There's a process, and it's called dehydration synthesis. So you might need to pause and write down the definition. But once you've done that, we actually can break down the words. So we all know what it means if we're dehydrated. If we are dehydrated, it means that there's been a loss or removal of water. So that word we are somewhat familiar with. Synthesis, maybe not so much. When I synthesize something, it means that I'm putting together or I'm building something else. So if we break down the words, we should be able to figure out what we're talking about in the words dehydration synthesis. And here are 2 kind of pictures of that. So each of these is a monomer, one here and one here. The plus sign means that I'm going to try to add them together. So guys, this is a chemical reaction. These are the reactants. This is the arrow. These are the products. Okay, so reactants always come before the arrow. Products always come after. I want you to take your highlighter and highlight this OH right here and this H. On my screen, they're red. On yours, they're just a slightly lighter color. So when I add these 2 together, guys, these monomers are kind of happy. They are complete. They don't need to bond with anything else. Like this one doesn't need to bond with this one, except that the cell wants it to. The cell needs it to. So what we have to do in order to make room for the bond that's occurring here is to remove some atoms to make space for the bond. And if I remove an OH and an H, that's going to give me H2O. So guys, the water doesn't disappear. It's out at the end, because really all a chemical reaction is we are breaking bonds and rearranging atoms. So I can't say that this oxygen and these 2 hydrogens disappeared. No, I've just taken them and from the original molecules they existed on and put them together to make a water molecule. So dehydration synthesis, water was removed in order to synthesize or build this material, this polymer right here. Same thing here, it's just a simpler version. So we have an H and an OH. If I want to join these 2 together, I need to remove it to make room for this bond. And here are the oxygen and the 2 hydrogens that I removed. So guys, with dehydration synthesis, water is always going to be on the side of the products. And we're always going to go from singular pieces to one larger structure. And why do cells do this? It's going to be a lot of reasons. To build molecules for your metabolism, to build more organelles. Your organelles are made out of all of these things that we're going to talk about. And to grow. If I need to grow, I need to be able to build more of my body. So all of these are reasons that we would be in the building phase, where we're linking monomers together to build polymers. But that's not the only thing we can do. So every time we eat, we kind of do the reverse of this. So I can break or digest polymers into monomers. So this is what hydrolysis is. We are breaking down complex polymers into simple monomers by the addition of a water molecule. So if we know that I had to remove water to build the polymer, I can't just start breaking things apart, because then I'd be missing atoms. So I need to add those atoms back in. I need to kind of give back what I took out. And we can break down this word too. The prefix hydro means water. The suffix lysis means to break. So I'm breaking something with water. And we're going to just have to learn to recognize these things, because all the kind of pictures can look a little bit different. So you have both of these pictures on your notes. So this is one larger structure right here in black. And right here, this little red bond is where this is one piece and this is a second piece. as you can see, water is being added into the chemical reaction, and now I have two monomers at the end. So I've taken a polymer and created this monomer and this monomer. And then down here is just another more simplified version. So we have, again, one polymer here because it has more than one piece. We put water in to break this bond and this bond, and then we have our two monomers here. We've returned the H that was stolen from this molecule and the OH that was stolen from this molecule. So the water literally goes back into the original molecules that it was taken from. Why do we do this? To recycle old cell parts. So sometimes cell parts get old and they need to be replaced, so we kind of break them down to start over again. And when getting energy from our food. So if you eat, this is what you're doing when you're digesting. You're taking things like really complex starch and breaking it down into its monomer so it's easier to digest. Proteins, you're doing the same thing. Fats, you're doing the same thing, because you need to then take those building blocks and build your own body with them. So hydrolysis and dehydration synthesis go together, meaning I do dehydration synthesis when I digest my food to get the monomers to then build my own body through I do hydrolysis. I feel like I said dehydration synthesis. I do hydrolysis to break down polymers into monomers when I eat, so that I get those monomers to do dehydration synthesis to build my own body. I know this can be a little confusing. We are going to practice this. I promise we're going to practice, and hopefully it gets a little less confusing. But something to note back here, if you're given a chemical reaction and you need to look at it to figure out if it's hydrolysis or dehydration synthesis, in hydrolysis, the water is always going to be on the reactant side. We need it to start, and it's not going to exist on the product side. In dehydration synthesis, the water molecule is always going to be on the product side because it was pulled out of the molecules. So that's an easy way to just start. You always got to look for the water. Where is the water that's going to tell you what's happening? But that's all the notes that you needed to do right now, so you can put that away. We're going to practice it more. I promise if you don't get it yet, hopefully in the next couple of days it gets a little bit more solid for you.